Hi, I'm Sagar Pali. In this presentation, I and Shaunak Mehta are going to summarize our work, Learning Latent Actions Without Human Demonstrations. Disabled people use wheelchair-mounted arms for performing their activities of daily living. The most commonly used interface for controlling the robot is a joystick. How do you get the robot to do what you want using just a joystick? One naive approach is to have a fixed mapping from inputs to robot motions. For example, one axis of joystick can control the robot motion in one plane. But if the robot knows what task it has to perform, it can assist the human in coordinating the arm's motion by learning a mapping from joystick inputs to meaningful actions. As shown in the video, pressing right on the joystick makes the robot place an object on a shelf. Assistive robots learn such mappings from human demonstrations, which could be provided by a non-disabled person, such as the caregiver. But a caregiver may not always be around. In fact, we want to reduce disabled people's reliance on others. So in this paper, we propose an approach to learn these mappings without human demonstrations. Our insight is that humans use assistive robots to interact with objects in the environment. Accordingly, even if the robot does not know the exact tasks it has to perform, it can still learn to manipulate objects in various ways. The first step of our approach is to train a reinforcement learning algorithm to learn policies that maximize object state entropy. That is, change object states in diverse ways. Using the trained policy, we collect a dataset of task-specific trajectories, which are then embedded to low-dimensional latent actions using an autoencoder. At runtime, we use the trained decoder to map joystick inputs to meaningful high-dimensional actions.
To test the efficacy of our proposed approach, we compare the latent actions trained using our method to those trained using human demonstrations. The humans provide demonstrations generally using two methods. The first is kinesthetic, where the human physically guides the robot to demonstrate the task. The second is teleop, where the human provides demonstrations using a joystick to control the end effector of the robot. Since the joystick inputs are more precise than the humans physically guiding the robot, the final state error for the latent actions trained using teleop is much lower than those trained using kinesthetic. As we add more noise to the demonstrations provided using teleop, the performance for the latent actions trained using teleop decreases as well. However, since our method does not require any demonstrations provided by the humans, it is immune to the imperfect or noisy data that it may receive. Due to this, its performance is comparable to that of teleop when the demonstrations are perfect. With our method performing well in these simulated environments, we move to see what happens when we deploy it in the real world. In a user study, we compare our method to the industry standard, that is, the direct end effector teleoperation. The first task in the user study is to clear the clutter in the environment to make way for it to complete other tasks. Next, the users need to move the bowl to a desired location. Once the bowl is in its desired place, the next task is to pick up the container and pour its contents in the bowl. Finally, the users need to dispose of the container. As we can see, with our method, the users were able to complete the task in much shorter amount of time as compared to the direct end effector teleoperation. We also observe that while working with our method, the users completed the task in less time with more consistent input on an average. This can also be seen in the plot shown below. Thank you. We are open to any questions that you might have.